Welcome, everyone. Today, we're going to explore the fascinating world of thermodynamic processes. This is the first slide of our presentation, titled Thermodynamic Processes. We'll start by understanding the basic concepts, and then dive into different types of processes that occur in thermodynamics. So, let's get started and discover how energy and work interact in various systems. Let's take a closer look at slide 2, where we start exploring the different types of thermodynamic processes and system properties. We'll begin with the concept of isobaric and isochoric processes. These describe how pressure and volume change during a process, either at constant pressure or constant volume. Understanding these helps us analyze how systems behave under specific conditions. Next, we have reversible and irreversible processes. Reversible processes are ideal. They can be reversed without any loss of energy, which is a useful theoretical concept. Irreversible processes, on the other hand, involve some dissipation, like friction or unrestrained expansion, making them more common in real-world applications. Moving on, we encounter the distinction between state functions and path functions. State functions, such as pressure, temperature, and internal energy, depend only on the current state of the system, not how it got there. Path functions, like work and heat, depend on the process path taken to reach that state. Then there's the cyclic process, which describes a system returning to its original state after a series of changes. This is fundamental in engines and other devices that perform continuous work. We also see the PV graph, which is a visual tool to represent all these processes, helping us analyze how pressure and volume change over time. Following that, the slide covers extensive and intensive properties. Extensive properties depend on the system size, like mass and volume, while intensive properties are independent of size, such as temperature and pressure. We'll also look into adiabatic processes, where no heat is exchanged with the surroundings, which are key in understanding rapid compressions or expansions. The W equals PV relation links work done to pressure and volume, providing a mathematical foundation for energy calculations. Isothermal processes maintain constant temperature, which simplifies analysis and is common in many industrial applications. Next, we have specific heat capacity, which tells us how much energy is needed to change a substance's temperature, an essential property in thermal analysis. Then, we examine conventions, which are standardized ways of describing processes and directions of heat and workflow, ensuring clarity in communication. Finally, the slide introduces the concept of different system types, setting the stage for understanding how different systems are modeled and analyzed in thermodynamics. All these points tie together to give us a comprehensive overview of the fundamental concepts in thermodynamics, which we'll explore in more detail throughout this presentation. Today, I want to talk about the fundamental difference between insulating and conducting materials. When we think about insulation, we're referring to materials that resist the flow of electric current. They act as barriers, preventing electricity from passing through easily. Conducting materials, on the other hand, are those that allow electricity to flow freely. They have free electrons that facilitate the movement of charge. Understanding these key points is crucial because, in our overall discussion on electrical systems, choosing the right material, whether insulating or conducting, can make a big difference in safety, efficiency, and performance. So, as we go forward, keep in mind how these properties influence the design and function of electrical components and systems. Now, let's take a closer look at diathermic systems. When we talk about diathermic, we're referring to how heat transfers through different materials or systems. It's a key concept because understanding how heat moves is essential in designing efficient thermal systems. Moving on to the types of systems, there are generally two main categories to consider. First, we have systems that allow heat to transfer freely. These are often called diathermic or conductive systems. They enable heat to flow easily through their materials. The second category includes systems that are insulated or designed to resist heat transfer. These are called adiabatic systems, which prevent heat exchange with their surroundings. Recognizing these types helps us understand how to control heat transfer in various applications, whether we want to maximize it, like in cooking or heating systems, or minimize it, as in insulation or refrigeration. So, in summary, understanding the difference between diathermic and adiabatic systems is fundamental because it directly impacts how we approach thermal management in engineering and everyday life. All right, now let's take a look at some other types of approaches that fall outside the main categories we've discussed so far. These are important because they show the variety of methods available, and understanding them can really enhance our overall strategy. When we talk about other types, we're referring to specific techniques or models that might not be as common, but are just as effective in certain situations. These can include alternative frameworks, emerging trends, or specialized tools that cater to unique needs. By exploring these options, we can better tailor our approach to fit different contexts and challenges. So, as we go through this, keep in mind how these other types can complement or even improve upon the primary methods we've covered earlier. It's all about expanding our toolbox and being adaptable in our solutions. Let's take a closer look at some additional types that expand on the core concepts we've discussed. These different types help us understand the variety and complexity within the subject. Each type highlights a unique aspect or approach, which is why it's important to recognize them. By understanding these variations, we can better see how they connect to the overall theme and how they might apply in different contexts. So, as we go through these, keep in mind how each type contributes to a fuller picture of the topic. This will help us appreciate the diversity and richness of the subject matter we're exploring. Now, let's take a closer look at some of the key properties that describe matter. First, mass, which is straightforward. It depends on the amount of matter present. Think of it as the measurement of how much stuff there is. Next, we have volume, which tells us how much space an object occupies. Then, moving into energy-related properties, we encounter internal energy, which is the total energy contained within a system, and enthalpy, which is essentially the heat content at constant pressure. Gibbs free energy is another crucial concept, especially when we consider spontaneity of reactions. Heat capacity measures how much heat is needed to change the temperature of a substance. Entropy is all about the disorder or randomness within a system. Finally, we have properties like energy itself, including specific forms such as internal energy and volume, which help us understand the system's state more comprehensively. Most of these properties can be classified as either extensive or intensive. Extensive properties, like mass and volume, depend on the amount of matter, meaning they change as you add or remove material. In contrast, intensive properties, such as temperature or pressure, remain the same regardless of how much material you have. Understanding whether a property is extensive or intensive helps us better analyze and predict the behavior of different systems in thermodynamics. Let's take a closer look at some key thermodynamic and solution properties. First, we have molar entropy, which reflects the degree of disorder or randomness in a system on a per mole basis. Moving on to molality, that's the concentration expressed as moles of solute per kilogram of solvent, a very precise way to describe solutions. Internal energy is another fundamental concept. It's the total energy contained within a system, encompassing all microscopic forms of energy. Viscosity measures a fluid's resistance to flow, which is crucial in processes involving fluid dynamics. Next, we have specific heat capacity, the amount of heat needed to raise the temperature of a unit mass by 1 degree. Normality and molarity are both ways to express solution concentration, but normality takes into account reactive equivalence, while molarity is simply moles per liter. Temperature, of course, influences many of these properties and is fundamental in thermodynamics. Refractive index tells us how light bends as it passes through a material, useful in various analytical techniques. Molar enthalpy is the heat absorbed or released during a chemical process at constant pressure, again on a molar basis. Mole fraction indicates the ratio of moles of a component to the total moles in the mixture, which helps describe solution composition. Concentration in general terms tells us how much solute is present in a given amount of solvent or solution. Pressure impacts many properties, especially gases and liquids under different conditions. Density, on the other hand, measures mass per unit volume and helps characterize substances physically. Now, an important point to remember is that many of these properties, like molar entropy, viscosity, refractive index, and molar enthalpy, do not depend on the amount of matter present. These are known as intensive properties. They're crucial because they remain constant regardless of how much material you have, making them very useful for characterizing substances in a consistent way. Understanding these distinctions helps us better analyze and predict the behavior of different systems in chemistry. When we look at state functions, it's important to understand that their values depend solely on the initial and final states of a system, not on the path taken to get from one to the other. For example, if you're considering entropy, Gibbs free energy, volume, internal energy, enthalpy, temperature, moles, or pressure, their values are determined just by where you start and where you end up. This means that no matter how the process unfolds, whether it's slow or rapid, complicated or straightforward, the change in these properties remains the same. This is a key point because it helps us focus on the overall change without worrying about the specific route. In contrast, there are path functions, which depend on the process path itself, but today we're emphasizing how these state functions give us a clear and consistent way to analyze thermodynamic changes. This concept is fundamental to understanding how energy and matter behave in different systems, and it connects directly to our overall theme of thermodynamic analysis. When we look at work and heat, they are a bit different from other thermodynamic properties because they depend on the path we take during a process. In other words, the amount of work done or heat transferred isn't just about the initial and final states, but also how we get from one to the other. This is what we call path functions. For example, if you're compressing a gas in different ways, the work done can vary even if the starting and ending conditions are the same. The key point here is that work and heat depend on the specific path, not just the endpoints. Understanding this helps us grasp the importance of the process details in thermodynamics, which ties back to the overall theme of how energy transfers and transformations happen in different systems. Let's take a closer look at the key points of a cyclic process. First, note that delta, the change in heat, is not equal to zero, meaning heat exchange occurs during the cycle. However, delta, the change in volume, is zero, so the process is carried out at constant volume. Moving on, delta, the change in temperature, is zero as well, indicating that the temperature remains constant throughout the cycle. Next, we see that delta, the work done, is not zero, which is a crucial point because work is being performed during this process. Conversely, deltas, the change in entropy, is zero, implying the process is reversible and there's no net increase in entropy over the cycle. Then, delta, the change in internal energy, is zero, which makes sense because, in a complete cycle, the system returns to its initial state. Finally, delta, the change in pressure, is also zero, maintaining constant pressure conditions. Putting this all together, the essence of a cyclic process is that the system undergoes a series of changes, but ultimately returns to its initial state, with no net change in internal energy or entropy, yet with work and heat interactions taking place. This highlights how energy transfer and work are central to understanding how cycles operate within thermodynamics. All right, let's dive into the concept of specific heat capacity. What we're looking at here are different ways to express how much heat energy is needed to change the temperature of a substance. First, notice the formulas for heat transfer at constant pressure and constant volume. When we're at constant pressure, the heat added Q relates to the molar heat capacity, Cp, through Q equals N times Cp times delta T. Similarly, at constant volume, Q equals M times Cv times delta T, where M is the mass and Cv is the specific heat at constant volume. Now, an interesting point here is the concept of the isothermal process, where the temperature stays constant. In that case, the molar heat capacity approaches infinity because no heat is needed to change temperature, since there's no temperature change. Next, let's look at the ratio gamma, which is the ratio of specific heats, expressed as gamma equals 1 plus 2 divided by F, where F is the degrees of freedom of the molecule. This ratio is crucial because it influences how gases behave during adiabatic processes. Speaking of which, under adiabatic conditions, the heat transfer, Q, is 0, so C adiabatic equals 0 for gases, meaning no heat is exchanged during the process. Now, focusing on water, the specific heat capacity C is approximately 4.2 joules per gram per degree Celsius. This tells us how much energy is needed to raise 1 gram of water by 1 degree Celsius. Moving on to molar and gram-specific heats. These are just different ways to measure the same property, either per mole or per gram. Finally, let's look at the table showing how the degrees of freedom, F, influence the heat capacities. For monoatomic gases with 3 degrees of freedom, Cv is 3.2 and Cp is 5.2, leading to a gamma of 5.3 or about 1.66. For diatomic gases with 5 degrees of freedom, Cv is 5.2, Cp is 7.2, and gamma drops to 7.5 or 1.4. And for polyatomic gases with 6 degrees of freedom, the ratios are slightly different again. Understanding these relationships helps us grasp how different gases store and transfer heat, which is fundamental in thermodynamics and various engineering applications. On this slide, we're looking at the PV graph for all the different thermodynamic processes. Let's start with the adiabatic process, which is represented here by delta equals 0. That means no heat is exchanged with the surroundings during this process. Because of that, any change in the system's internal energy results solely from work done on or by the system. Next, we see isochoric processes, where delta equals 0. This indicates that the volume remains constant throughout the process. In such cases, since the volume doesn't change, the work done is 0, but the temperature and pressure can still vary depending on the heat added or removed. Moving to isothermal processes, which are characterized by a constant temperature, so delta equals 0. Here, the pressure and volume change, but the temperature stays the same. This typically results in a hyperbolic curve on the PV diagram, reflecting the inverse relationship between pressure and volume. And finally, the isobaric process, where delta equals 0. The pressure remains constant in this process, but the volume and temperature can change. It's often represented by a horizontal line on the PV graph. Connecting all these points, the key takeaway is that each process has a unique signature on the PV diagram, helping us visualize how pressure, volume, and temperature interact during different thermodynamic changes. Understanding these differences is fundamental to grasping how energy transfer and work are involved in each process. Let's talk about reversible processes and why they are considered not very practical. First, they tend to be slow. Because each step in a reversible process occurs in equilibrium, the entire process must proceed very gradually. This means that the change happens in infinitely small steps, essentially taking an infinite amount of time to complete. The equation W equals integral px dv highlights that work is done during this process, but because it's so slow, it's not feasible for real-world applications. The key idea here is that reversible processes are idealized. They are conceptually perfect and involve no entropy production, but in reality, they're just not practical for everyday use. This is why most natural and engineering processes are irreversible, even though reversible processes are important for understanding the limits of efficiency. Let's take a closer look at this practical situation. The key point here is the work done, which is expressed as W equals negative sigma P delta V. This means that the work depends on the pressure and the change in volume. Now, in this scenario, we're considering an equilibrium state that exists initially and then again finally. Importantly, this process is fast, occurring almost instantaneously. When I say it occurs at once, I mean it happens in a finite time, not gradually. This kind of process is typically irreversible, meaning it can't simply be reversed by revering the process. And because it happens in a finite time and is irreversible, it's usually associated with sudden, non-equilibrium changes. These points are crucial because they help us understand how work and energy transfer happen in real-world dynamic systems. This slide ties into our overall theme of analyzing real processes versus idealized ones, emphasizing the importance of understanding the nature of these rapid, irreversible changes. All right, let's talk about the conventions related to work and heat in thermodynamics. When we say work done by a system is negative, that means the system is doing work on its surroundings. Think of a gas inside a piston expanding. It's pushing outward, performing work on the piston. So from the system's perspective, that's work done by the system, and it's considered negative in this convention. Similarly, when heat given by the system is negative, it indicates that the system is losing heat to its surroundings. So, if the system cools down by releasing heat, we record that as a negative heat transfer. On the other hand, when work is done on the system, meaning external forces are doing work into the system, that's positive. For example, compressing a gas increases its internal energy, and we mark that as positive work done on the system. And when heat is given to the system, that's also positive, showing that the system is absorbing energy from its surroundings. These conventions are crucial because they help us maintain consistency in our analysis, especially when applying the first law of thermodynamics. They connect directly to the overall theme of energy transfer, whether it's work or heat, and how we quantify these processes. So, understanding and applying these sign conventions correctly is key to analyzing thermodynamic systems accurately. All right, let's talk about the concept of work, represented as W in thermodynamics. When we see a positive W, that indicates compression, meaning the system is doing work on the surroundings. Conversely, a negative W corresponds to expansion, where work is done on the system. Now, the general expression for work done during a process can be written as the integral of pressure with respect to volume. So W equals the integral of P dV when we consider the external pressure, Px. The work becomes negative of that integral, or W equals minus the integral of Px dV. This is often visualized as the area under the PV graph, which is a helpful way to understand the work done during a process. The negative sign appears by convention because of the way we define the work done by or on the system. To connect this to force, recall that Px equals F divided by A, where A is the area. Rearranging, F equals Px times A when the object moves a distance delta x. The work done by the external force is F times delta x, which simplifies to Px times A times delta x since delta V equals A times delta x. The work becomes minus Px times delta V. Finally, let's touch on the PV relation. This relation is fundamental because it links pressure, volume, and work, helping us understand various thermodynamic processes in a straightforward way. It's a key point in analyzing how energy transfer occurs during expansion and compression. Let's talk about the sign convention for work in cyclic processes. When the work is positive, it means it's done in the anticlockwise direction. Conversely, if it's negative, as in this case, it indicates the work is done clockwise. Remember, the net work, Wnet, is represented by the area enclosed by the cycle on the PV diagram. So in essence, the net work corresponds to the area inside this shape. Now, focusing on this slide, which illustrates a cyclic process, the key point is that the direction of the cycle, whether clockwise or anticlockwise, determines the sign of the work. A clockwise cycle typically indicates work done asterisk by the system, like during an engine cycle, while an anticlockwise cycle usually means work is asterisk done on asterisk the system. Understanding this sign convention is crucial because it helps us interpret the energy transfer during these processes. The area enclosed by the cycle visually represents the net work done over the entire cycle, linking the graphical representation directly to the physical work interaction. This concept ties back to the overall theme of energy transfer in thermodynamic cycles. emphasizing how we analyze these processes both visually and mathematically to get a clear picture of what's happening energetically. Let's take a look at some specific processes now. First, consider vacuum or free expansion, where the external pressure is zero. In this case, since there's no external work done, we say W equals zero. Essentially, the gas expands into a vacuum without doing any work on the surroundings. Next, we have the isochoric process, which is characterized by a constant volume. Since the volume doesn't change, the work done is zero because work is related to volume change. Now, moving to the isobaric process, where the pressure remains constant. Here, the work done depends on the change in volume, and it's calculated as negative P external times delta V. The key idea is that the work is directly related to how much the volume changes when pressure stays the same. Connecting these concepts back to the overall theme, understanding how different thermodynamic processes involve work helps us analyze energy transfer in various systems. Recognizing the conditions, whether volume, pressure, or external forces, allows us to predict the work done during these processes. Now, let's look at the key equations that describe the work done during an isothermal process. First, we see that the work W can be expressed in terms of pressure and volume changes, involving logarithms of the ratios of the final and initial states. Specifically, W equals negative P1 times V1 times the log base 10 of the ratio V2 over V1, which is equivalent to negative P2 times V2 times the same log ratio. But to connect this to the ideal gas law, we can rewrite it in terms of the number of moles, R, temperature T, and the pressure ratio, leading us to the expression W equals negative 2.303 times nRT times the log of P2 over P1. Similarly, we can express the work in terms of volume ratios, substituting pressure with volume using the ideal gas law, resulting in the same form, but involving the ratio V2 over V1 instead. Finally, the last equation highlights the integral form of work done during an isothermal process, where the external pressure is constant. Integrating from V1 to V2, the work equals negative nRT times the natural log of V2 over V1. The key takeaway here is that, in an isothermal process, the work done depends logarithmically on the ratio of final to initial states, and since temperature remains constant, the internal energy change is zero. This ties back to our overall theme of understanding how gases behave under different thermodynamic processes. All right, let's wrap up with the concept of an adiabatic process. An adiabatic process is one where no heat is exchanged with the surroundings. This means that all the energy change in the system is due to work done on or by the system itself. It's a key concept because it helps us understand how systems behave when they are perfectly insulated. In real-world applications, perfect adiabatic conditions are idealized, but many processes, like rapid compression or expansion in engines, closely approximate this idea. The most important point here is that in adiabatic processes, the temperature and pressure of the system can change significantly even without heat transfer, simply because of the work interactions. Connecting this to the overall theme, understanding adiabatic processes is crucial because it underpins many thermodynamic cycles and efficiencies, especially in engines and refrigeration systems. So, by mastering this concept, we gain valuable insights into how energy conversion efficiencies can be optimized in real-world systems.